make it work. So you can see on the left here is part of the IBM key punch. It's a great long thing. You can see a computer of average transients, which is actually built by Varian, had 1,000 channels. And you see Richard on the right pretending to readjust the machine. And they produced a result. They got a much better spectrum by Fourier than by sweep, so this is the answer to our dreams. Notice they didn't claim an order of magnitude improvement. They didn't claim a factor of 10 improvement. They claimed a factor of 10.0. Okay, that's Richard. I want to make a phase jump in time, a time warp here, plus 40 years to get away from that old stuff because you're getting bored with that. What about 2003? Now, I felt it was a terrible shame that West's experiment was never vindicated. It was never actually tried in practice. And then I thought, well, look, technology's improved so much in those 40 years. Why don't we just try this? Why don't we do it? Why don't we re-examine the multi-channel irradiation scheme? And again, I was very lucky because I had Eric's, I think you all know Eric's Kupchi, he's everywhere. Organometallic chemist from Riga, from Latvia, who took up NMR, taught himself NMR, and has been inventing new experiments ever since. So the first part of the problem is solved. We can do multi-channel irradiation because Eric's has been working on this for some time. Now we need to disentangle the results, which is another problem. We have this nice French guy, Jacques, who invented the Hadamard matrix, which is sometimes drawn as pluses and minuses. Now, how is this going to help us? Well, just let's, for example, think we have 8 non-equivalent spins for some reason. We want to irradiate all the sites simultaneously with soft radio frequency pulses, which I'll show as a series of Gaussians here. And let's see what happens. In the first scan, we collect all the free induction, we collect a free induction decay of all the positive peaks, but then in the next scan, we change some of the signs of the pulses, and as we go on, we change these in a pattern which you all recognize as being a Hadamard matrix, and we have to complete 8 of these experiments, otherwise the method doesn't work at all. So in the 8th one we have this 8 by 8 Hadamard matrix, and then we combine 8 of these FIDs according to one of the columns of the matrix. Let's suppose that's the red column, that we just alternate the free induction decays, and that detects only the response from the third site, number 3, the red one here. If you think about it, the signals from all the other channels disappear identically. This is the magic property of a Hadamard matrix. Here's strychnine again. I must say, Eric surprised me. He went away, did an experiment with 2,048 individual excitations. And if strychnine was going off a bit here, as you can see, but if you try to compare these two spectra, it's really impossible to say which is conventional, which is Hadamard. The spectra are essentially identical, so it worked extremely well. One problem, I seem to be always saying this, one problem is you need to do 2,048 scans. So it's not all that practical. I mean, there are applications of this, but which I won't go into, but this is not a very practical experiment. It was never meant to be. It was a test. And I always said to my students, never abandon in practical experiments. They could turn out to be useful. All you have to do is to expand them a little bit, and in this case, we've considered two-dimensional NMR, which you all know about. You evolve for a time t1, you detect for a time t2, you do a Fourier transformation in both dimensions, you get a spectrum. Fine, everyone knows this. The alternative mode, which we tried, was to excite with a set of radio frequency selected pulses, and we get the same spectrum. It's not such a daft experiment, actually, because it doesn't take any longer than the conventional two-dimensional method, but its sensitivity is way down because it doesn't have the multiplex advantage. But you can get around that if you know the chemical shifts. And you know the chemical shifts because you can do a quick 1D experiment and measure them. So then you can do a Hadamard encoded multi-channel excitation. In this case, you only need 4 excitations, and you encode them according to this little scheme here, and you get the same spectrum, and it's much faster. Let me show you a typical small molecule. Well, you can see the atoms. It's actually an extremely small protein, so I think I can sneak it into this meeting. And we got it for free anyway, so... Suppose we do a 3-dimensional experiment on globally enriched N15 C13 agitoxin, and we project it on the carbon-proton plane, so we have all these responses here. But let's suppose that we were really interested in specific isotopic enrichment, which is much more expensive to do. So we pick out these amino acids that have got the arrows on them and say, these are the ones we're interested in. We're not interested in the rest. So then we do a Hadamard experiment. I think it will do a Hadamard experiment. There you go. You lose all the other responses and you get the ones that you chose, and you have a speed advantage of 200. So here Hadamard is actually working to our advantage. And that speed advantage can be traded off for something else. If we're interested in high resolution, we're interested in NH splittings, for example, we can measure 8 of those in one shot. Now you may say, why would we bother with NH splittings? Well, this is an isotropic solution, but if we had a partially oriented solution, then we could measure the residual dipole splittings, and this would tell us about orientation of the molecule. So by using the Hadamard method, you could get accurate measurement of these couplings, which could be modified by the dipolar coupling. Or you could use the time to measure dynamic effects. 7 sites were measured at the same time. Only the glycine 47 is shown. And you measure the T1 as, in this case, about half a second. But the experiment I've always liked is to use carbon-carbon correlation in natural abundance small molecules. And if you lecture on this, it's guaranteed that someone in the audience will say, well, what about sensitivity? Okay, what about... Sensitivity is inadequate. That's why we called it inadequate, for God's sake. But we have a trump card here. We have Jacques, the Vallée de Cahos, and we can use the Hadamard method to measure these. Now, I'm sorry about the product operators. It's a bit late in the evening for those. But it's the only way to show that if you irradiate one of the spins with an X pulse, you get an S spin signal, the one that's in orange here. And if you irradiate an S-spin signal, you get an I-spin signal. So you get two complementary measurements of the same thing. If you get signals, it means those two carbons are directly bound together. This is the beginning of the inadequate experiment. If you get no signal, they're not coupled, they're not close to each other. Well, I thought I'd frighten you a little bit here. What I call the nightmare scenario is this. What happens when machines start to think for themselves? Watch his eyes. Machines are getting cleverer, smarter every day, and we're at a plateau. So you don't have to plot a graph to realize that one day we're going to be in trouble. Well, we don't want to go down that path tonight. I just want to take one small step along that idea, is to say, supposing we have NMR sequences that choose their own operating parameters. It's the same idea, but it's not as dangerous. And now we have NMR spectrometers with up to 4 separate receivers. So you can be measuring something here and at the same time using that information for setting up an experiment there, and so on. Not sure what comes next. Oh, you measure a 1D C13 spectrum. This guy selects the C13 frequencies for you. He encodes them with a Hadamard matrix. He sets up multiple irradiation of all of those sites, and he detects the I to S and the S to I transfers. He reassembles these in the form we used to have for inadequate, because now we know what the double quantum frequency would have been, because it's just the sum of the two chemical shifts. And you get the carbon framework. So we don't need any chemists anymore. We don't need small molecule people. This guy is going to do the whole thing. Let me just show you it at work. We have an inadequate experiment done by this different method, the carbon framework. So every horizontal bar on this is detecting a CC bond, which is being shown on the left. And it just goes on and it produces the well, at least the basic framework of the small molecule. And actually the experiment takes a factor of about 2 longer than it took to do this animation. And there it is in the normal form. It's menthol, 30% in deuterochloroform. It took only 56 seconds, less than a minute. So inadequate isn't yet dead. That's the story I want to pass on to you. And these are the people I was trying to promote here. Rex Richards, for obvious reasons. Anatol Abragam, who unfortunately died only a few weeks ago. A tremendous intellect and a great joker. When I worked in his group, if we had visitors, he would show them around and then he'd say, "Oh, this is Ray. We keep him just to calibrate our English." Now you may think, well, that's pretty innocuous. But the word for calibration standard in French is étalon, which is also the word for stallion. So he was saying, this is our English stallion. And you could never have a discussion with Anatole without him pulling some trick like that. I give him a French flag because he spent most of his time in France, but of course he was of Russian origin. Bob Pound was actually a Canadian, good for Bob. Bob actually missed the Nobel Prize on 2 occasions, which was very sad. Okay, again, the Gedanken experiment, but if Bloch's group had not discovered NMR simultaneously, the 3 people at Harvard would have shared the prize, and one of those was Bob Pound. When he left Saclay, he went back to measure the gravitational redshift using the Mossbar effect, who, in my opinion, should have had a Nobel Prize for that, and they gave it to Mossbar instead. Wes Anderson, again, you've seen his influence all the way through this talk. Richard Ernst, everyone knows. I mean, the only reason I'm a little bit sorry, I never actually collaborated with Richard except on 2 small papers. I was just a spectator when he did this marvelous work on the Fourier transform. And then finally, but not least, Eric Kutchi from Latvia, who has been doing clever NMR experiments for the last 20 years. Thank you for your attention.